so we're going to do the last part, the D part, in this video. And this question is asking, what is the pH when the volume of sodium hydroxide solution has been added that is equal to half the amount to reach the equivalence point? So we know from the previous problem that to reach the equivalence point, you need to add 1 liter of the sodium hydroxide. So halfway to the equivalence point, the amount of sodium hydroxide that would have been added at that point would be 500 mils. So let me go back to here. Okay, so let me get myself squared away here. So the first thing I'm going to mention here is that at this point, the volume of NaOH added will be equal to 500.00 mils, all right? Which means that the moles of sodium hydroxide added at this point will be equal to 500.00 mils times 1 liter over 1,000 mils times the molarity, which is 0.100 moles per liter. So when I work this out, I got 0.0500 moles. So I'm going to write, of course, the equation for the reaction between the acid and the base to form NaA plus H2O. And then I'm going to start off with initially writing down the moles of the acid and the base, which in the case of the base is going to be 0.0500 moles, whereas in the case of the acid it's going to be 0.100 moles. And here you're going to have none of that. Again, you don't need to concern yourself with water. The change here would be that since sodium hydroxide is a limiting reactant here, it will be completely used up here. The same amount of HA in terms of moles would be used up here, and here you're going to have okay, I think I made oh everything's fine. So here you're going to have plus 0.0500. Again, you don't need to worry about the water, so at the end of the reaction you're going to have 0.0500. You're going to have 0 here. You're going to have 0.0500 here. Next thing, of course, is to determine the concentration. And it turns out that in this case, the concentration of HA will be equal to the concentration of A minus. Why? Because they have the same moles and they're in the same solution, which means that they have the same volume. So that would be equal to 0.0500 moles. And the total volume, let me do it over here. The total volume would be equal to the 1.00 liters from the acid plus the 500 mils, which is 0.50000 liters from the base. So this works out to be equal to 1.50 liters. So we're going to divide by 1.50 liters here. And according to my calculation, this works out to be 0.0333. Now, the thing is that this is not really even necessary for us to know the concentration of either the weak acid or the conjugate base. It's only important that we know that they're equal to each other. And the reason why is because when you plug the numbers into the Henderson-Hasselbalch equation, pKa plus log of concentration of base, A minus, over the concentration of acid, HA. Because these two are equal, A minus and HA, that means that this part here will be equal to 1. And log of 1 is going to be 0. So therefore the pH is simply going to be equal to the pKa of the acid. And the pKa of the acid is minus log of the Ka, which is 1.80 times 10 to the minus 5, and that pKa works out to be equal to 4.745. And that's basically how we do that. And this is actually the method very often used to determine the pKa of an acid. Basically, you do the titration until you get to halfway to the equivalence point, and then you measure the pH at that point, and that pH will be equal to the pKa of the acid. And based on that, you can determine what the Ka of the acid is. Okay, so that's basically it for these series of questions. I thought it was important that I go through each and every one of them so you get a good feel for, the type of questions that you could encounter in your tests, quizzes, etc. All right, so the next video, I'm going to deal with acid-base indicators. I kind of alluded to them earlier in terms of how they're used in titration. You're going to have a better understanding as to how indicators work and how they're useful when it comes to certain titrations. All right, until next time.